In this lesson, I'll show you 3 examples involving stoichiometry and the change in enthalpy. Question 1 reads, a liquid petroleum gas tank in a home barbecue contains 13.2 kilograms of propane, which has the chemical formula C3H8. Calculate the heat Q in kilojoules associated with the complete combustion of all the propane in the tank. The complete molecular formula for the reaction is shown right here, and we're told that the change in enthalpy represented by delta H for this reaction is negative 2044 kilojoules per 1 mole of propane. This question is actually quite simple. All we have to do is use the molar mass of propane along with the conversion ratio that 1,000 grams is equal to 1 kilogram to find out what we're looking for. I'll take my mass of 13.2 kilograms and convert it into grams. Once I've done that, I'll use this number along with this number to find out the kilojoules. Let me show you. I'll take 13.2 kilograms multiplied by 1 kilogram equates 1,000 grams. This will give me the number of grams, my mass in grams. Once I've done that, I'll multiply the product of these two by 1 mole per 44.09 grams. The reason why I'm doing it this way is so that this unit, the grams here and the grams here, cancel out, leaving us with moles. Once I have the number of moles, I can then multiply the product of these 3 factors with negative 2044 kg per 1 mole of C3H8. Now the mole unit cancels out, and we're left with exactly what we're looking for. Let's use our calculator to do this. We have 13.2 times 1,000, this times 1 times negative 2044 times negative 2044. This gives us a very large number as expected, and we'll divide that by 44.09 grams. This gives us a total Q value of negative 611,948. We only want 3 significant figures because this number contained 3. So I'll write this down as negative 6.12, I've rounded this 1 to a 2, times 10 to the power of 5. Negative 6.12 times 10 to the power of 5 kg. Moving on to question number 2, we do something very similar. This time they want us to calculate the heat Q in kilojoules for the following reaction. Since we're already accustomed to doing this, we can do it a lot faster. I'll take 155 grams, which is the amount of ammonia reacting with oxygen. I'll multiply this by 17.04 grams at the bottom and 1 mole at the top, and subsequently multiply that by this number, negative 906 kg per mole. 155 times negative 906 divided by 17.04 gives me my final kg answer. That's negative 8241. We should only have 3 significant figures. Negative 8.24 times 10 to the power of 3 kilojoules. Lastly, in question number 3, they ask what mass of butane in grams is necessary to produce 1.5 times 10 to the power of 3 kilojoules of heat. This question is a little more tricky than questions 1 and 2 because now they're looking for the mass of butane and then subsequently the mass of carbon dioxide. To do this problem effectively, you have to understand that 1.5 times 10 to the power of 3 should be represented with a negative. The reason why is because this is the amount of joules being produced. That means it's being released. So we have to write down negative 1.5 times 10 to the power of 3 kg. We then take this number and multiply it by the flipped version of this fraction. Because by reorienting this fraction so that we have 1 mole at the top and negative 2658 at the bottom, the units for kg will cancel out, leaving us only with the number of moles. Let's find out what that is. The number of moles of butane. Negative 1.5 times 10 to the power of 3 times 1 divided by negative 2658. This gives us 0.5643 moles. 0.5643 moles. This will play an important role when we answer this part of the question. If I multiply the product of these two, by the molar mass, and this should read butane. The molar mass of butane, where I have 58.12 grams at the top and 1 mole at the bottom, I'll end up with the mass of butane because this mole unit and this mole unit cancel out. So I'll take this number and multiply it by 58.12, and this gives me the mass of butane at 32.79 grams. 32.79 grams. They want us to find the mass of carbon dioxide produced. We need to create a mole ratio here. We have 1 to 4 ratio, and the moles of C4H10 were found earlier. Remember I said this will come in handy. I'll place that number right here. And I need to find out the equivalent amount of moles for CO2. I'll cross multiply, taking 0.5643 times 4 gives me the number of moles of CO2, 2.25. 2.25, and I'll take one more digit, 7. All I do to find the mass of CO2 is take this number and multiply it by the molar mass of CO2. The molar mass of CO2 can be found by taking 12.1, the molar mass of one carbon atom, plus 16 times 2, 44.01. Multiply this by 2.257. That gives me 99.3 grams of carbon dioxide produced. Mass of CO2 is 99.3 grams. And there you have it. 3 examples on how to solve stoichiometry problems involving the change in enthalpy.